So what you're looking at are the backsides of two jet engines. When I look at these, I see what we would call a nozzle. And the whole point of the jet engine is to accelerate the air rapidly behind the airplane. So it accelerates the air to the back of the airplane, and there's an equal and opposite force of the air on the engine that drives the airplane in the forward direction. The only point of the nozzle is to accelerate the air, is to increase the kinetic energy of the air. So keep that in mind. When we talk about nozzles, the only reason we're using it is to accelerate a fluid. So one example is the jet engine. Other examples would be a garden sprinkler, for example. You want to accelerate the water into the field for the plants that you're trying to water, or maybe a fire suppression system trying to throw the water a great distance, or a nozzle on a fire engine also comes to mind. Maybe you want to accelerate a fluid and then splash that, impact that on a paddle wheel perhaps, and you want a high amount of kinetic energy going into the paddle wheel to turn the paddle wheel, or a different type of turbine. In any case, the principle behind a nozzle is the decrease in the cross-sectional area. So if we look at a simplified diagram, we've got a large cross-sectional area here where the fluid enters and a narrowed cross-sectional area where the fluid leaves. If we call this stream 1 where the fluid enters and stream 2 where the fluid leaves, what we'll find is that V2 is larger than V1. It increases its speed because the cross-sectional area is decreased. By way of a mass balance, we've got the mass flow rate entering the nozzle is equal to the mass flow rate leaving the nozzle. And that's always true, regardless of whether or not the fluid or the gas changes density. The mass flow rate is equal to the density at 1 multiplied by the volumetric flow rate at 1 multiplied by the density and the volumetric flow rate at 2. Because the density is the inverse of the specific volume, we could say it's V dot 1 over V hat 1 equals V dot 2, the volumetric flow rate at 2, divided by its specific volume. And volumetric flow rate is equal to the speed at location 1 multiplied by the cross-sectional area at 1 divided by its initial specific volume, and we'll say that's also equal to V2A2 divided by its specific volume. And this forms the crux of what it takes to solve problems involving a nozzle. If, for example, the fluid was incompressible, that means that its specific volume would be the same on both sides, and we're left with the relationship you're familiar with, V1A1 equals V2A2. Well, let's think of an energy balance around the nozzle itself. First off, there's no work being done. There's no shaft, it's not rotating anything, there's no, our work terms are 0. Let's also assume that it's adiabatic, so there's no heat flow, so the values of Q are 0. The only thing that we've got is internal energy entering at location 1, so I'll say m dot 1 multiplied by the internal energy at state 1, and this is going to be easy to forget, but we also have flow energy entering at 1, which is equal to m dot 1 p1 v1. And we don't have any potential energy entering at 1 because the elevation of the nozzle at 1 and 2 are basically the same, so there's no gravity involved with this. The only other form of energy that we're bringing in to location 1 is kinetic energy. So that's going to be equal to 1/2 m dot 1 v1 squared is the rate at which kinetic energy is entering the nozzle. We've got internal energy leaving at location 2, so m2 dot u2. We've got flow energy leaving, m dot 2 p2 v hat 2. And of course we've got kinetic energy leaving at state 2, which is 1/2 m dot 2 v2 squared. So there's a couple of ways we can dramatically simplify this equation. One thing to recognize is that, well, the mass flow rate entering the nozzle has to equal the mass flow rate leaving the nozzle, so m dot 1 is equal to m dot 2. So because they're equivalent, we can cross these off of both sides of the energy balance equation. The next thing that's handy is, so we don't have to deal with both internal energy and this PV term, another thing that's handy is we'll make the substitution and call that enthalpy. So we're left with H1 is plus 1/2 times the V1 squared is equal to H2 plus 1/2 V2 squared. So this is what I would call an energy balance for a nozzle. So the rate at which enthalpy enters plus the rate at which kinetic energy enters equals the rate at which enthalpy leaves plus the rate at which kinetic energy leaves. Another way to say this is that the fluid flowing through the nozzle has gained kinetic energy at the expense of the fluid's enthalpy. And because the whole point of a nozzle is to increase the speed of the fluid, that necessarily means that H2 has to be less than H1. In other words, delta H has to be less than 0. Now, if you're working with an ideal gas, don't do this for steam, but if you're working with an ideal gas, delta H is equal to Cp delta T. So that says that Cp delta T is less than 0, which means that T2 is smaller than T1. So the gas gained kinetic energy at the expense of its enthalpy, and because enthalpy for an ideal gas is associated with its temperature, that means that the temperature of the ideal gas leaving at location 2 is cooler than the temperature entering at location 1.